scientific notation and then moving to the left or the right is what changes that exponent n, right? So we have the two components for scientific notation. We have a, which is our coefficient. That's a number that has to be between 1 and 10. And then we have n, which is our exponent. It's going to be an integer, which means it's a whole number. It's going to be positive or negative, right? And that tells us the magnitude or the size of the number. The coefficient tells us the identity of the number. Like, that's the actual number itself. All that information is coded in there. And we talked about, okay, well, if we have a large number, how do we convert that to scientific notation? If we move decimal places to the left, then we're going to be having a positive exponent. The number of decimal places we move, that tells us what the exponent is going to be, right? The integers left over, that's what our coefficient is, right? So we move the decimal place over until we reach a number that's in between 1 and 10, right? So here's like, what is this, 1, 2, 3, so 75 million, right? We have to move it 7 spots over, and now it's 7.5, and these are all the zeros that come after that. But we had to move it 7 spots over, which is why n is equal to 7 there. Okay, here, let me put this down. And then for the opposite trend, for a small number, right, we move the decimal place to the right. That means it's going to be a negative exponent. It starts off at 0.00642. We want to move it until it's a number between what? 1 and 10, right? So we move it over 1, 2, 3 spots. So then it becomes 6.42. And we multiply it by 10 and move it to the right. So it's negative 3 spots over, right? All right, any questions on that? All right, and again, this is because all we're doing is we're writing the exact same number. It's just an easier way, right? This number isn't that hard to write in normal notation, but if it's 10 to the 23 or 10 to the minus 23, you don't want to write 0 23 times, right? So this is a way to make this simpler. And also, once we get to calculations, it's a way that we can simplify doing calculations with large and small numbers. Okay. And so, are you guys able to hear me back there okay, or is it kind of hard? All right. It's a little hard? Yeah, I know. I'm yelling at max capacity right now. My voice doesn't get very loud. I tried using this before, and it never worked. And I asked for a microphone in here, and then it never worked. I'm not going to be lecturing in lab a whole lot, hopefully, so hopefully it's just for today. But if you don't hear anything, don't hesitate. I'll come over and I'll yell it over there to let you guys know. Okay, so calculations with scientific notation, right? So we change the number. The first thing we're going to do is change the number into the exponential form. This just means in scientific notation, we multiply or divide the coefficients. This is mostly going to be doing multiplication and division, right? So with the order of operations, when you multiply things, it doesn't matter what order you multiply things, right? You can multiply any two things together. So if you have something like, and I'm going to do a times 10 to the 3 multiplied by b times 10 to the 5, right? We can rewrite this. This is the same thing as saying a times b times 10 to the 3 times 10 to the 5, right? We can rewrite this in any order we want to. So the second step, what it's saying is that, well, the easiest thing to do is just multiply the coefficients first, right? And that's what you plug into your calculator. Then we add exponents if we're multiplying, or dividing exponents, or subtracting exponents if we're dividing. And so, well, what does that mean? Well, if we have a number, I'm going to use some arbitrary number, like a to the 3 times, we'll use a to the 5, right? So this is two things. One a is raised to the power of 3, and the other one is raised to the power of 5, right? The way this simplifies is this is equal to a to the 3 plus 5, or a to the 8th power, right? So that's just a rule. That's an identity with exponents. You don't have to worry about where that comes from, but that's just a rule. If you're multiplying things that are the same base, right? This is the base here. And they, with different powers, the powers either add or subtract, depending if you're adding or dividing. So conversely, if you were dividing and it was a to the 3 over a to the 5. That's the same thing as a to the 3 minus 5, which equals a to the minus 2. Right? So when we're multiplying, we add them together. If we're dividing, they subtract with each other. And a here is just any arbitrary number, right? So when we're using scientific notation a lot of the time, it's going to be base 10, right? So you have 10 to the 3 times 10 to the 5 is going to be 10 to the 8, is how those will simplify. All right, and then the last step says, if needed, we reconstruct the answer. And so what does that mean? Well, if we have something like 3 times 10 to the 5 times 5 times 10 to the minus 2, something like that. We first multiply the coefficients together. And I know it's low, so it's kind of hard to see. Like I said, I'm going to try not to be lecturing in here that much. It'll be 3 times 5 times 10 to the 5 times 10 to the minus 2, right? So all I did was I just changed the order of how things are listed. I added the answer there. 3 times 5 is what? 15. So it's 15 times 10 to the 3, right? Because 5 plus negative 2 is 3, right? It's the same thing as 5 minus 2. So the same thing as 5 minus 2. And so what's wrong with our final answer here? Yeah, the coefficient needs to be between 1 and 10, right? Which means we need to adjust this so that it's between 1 and 10. So we do the exact same thing, right? So in purple, I'll put adjust. So right now the decimal place is right here. We move the decimal place for 15 to the left or to the right here. I'll write it on the board too. So we have 15 times 10 to the 3, right? Initially, our decimal place for this coefficient is right there, right? We want to make it in between 1 and 10, so do you move it to the left or the right? The left, right? So we move it to the left, and whenever we move something to the left, how do we account for that in the exponent? How do you guys think? Positive, right? When we move it to the left, it has to go up because it's becoming a more positive number. So what do you think we do to 3 there? Yep, we add 1 to that, right? So this is 1 spot. So we plus 1 there. So it becomes 1.5 times 10 to the 4. If you left it like this, I'm really, if I did take any points off, it'd be very, very minor unless the question is specifically asking about scientific notation, right? Because really that's not that big of a difference from that. But this is technically the correct scientific notation for that number. All right, so I'm just going to put that on the slides here while you guys think about that for a second. And I just erased everything. All right, so that's going to be 1 spot plus 1. 1.5 times 10 to the 3. And I'll probably do that for the next couple slides. So I'll probably put it on the board there. I'll move over there so you guys get equal. Let me ask Jimmy if it's okay if I erase the equals over. Any questions on that, right? So this adjustment, right? Whenever we move it to the left, it's like we're dividing it by 10 because we're making the smaller number. And to make the number the same, we have to multiply it by 10 as well, right? So you're just adding it times 10 to the 1 here. So you get 10 to the 3 plus 1. That's where that plus 1 comes from. Right, so there's a number of different ways you can think about this. I'll try and explain it every way, so whatever way resonates with you to make it work. Right. All right. Any questions on that? Yeah. So I'll post all once we're done with this. So we'll probably finish this today, calculations and review of math and stuff like that. So I'll post that on Canvas. So these are the slides already posted, and then once we're done with those slides, I'll post the completed version to Canvas as well. All right. Sorry. You only need the lecture notes to probably get through everything that I'm going to give you. It'll be heavily based off of that, but whatever extra resources you want to use, you're more than welcome to. It's there's only so many ways that you can remake the wheel, right? So yeah. But I'll give you guys extra practice problems. The book will have extra problems. If you want to go through the book and look at some of the problems, you want to bring them to me, I can go over them with you and stuff too. Okay? Yeah, pretty much like the lecture notes and what we cover in lecture is really all I'm never gonna ask you anything that I haven't covered in class. Okay. Good questions. Okay, so here we have a simple example. Multiply 30,000 by 600,000 without a calculator, right? So you can do this just with scientific notation. We can simplify the calculation quite a bit doing that. I'll give you guys this one first. Divide 30,000 by 0.006. All right, so I'll write that up here. 30,000 divided by 0.006. So divide those two numbers while I fill out the other slide. Okay. So the first step, again, was to do what? Convert. So 30,000, we already did that one. Right, that was 3 times 10 to the 4. What about 4.006? What's that going to be? Yeah, it'd be 6 times 10 to the negative 3. How do we get there? We decimal place starts here. We move it 1, 2. We're still less than 1 there, right? So we have to be in between 1 and 10. Move it over one more time to right there. So now we have the coefficient, which is 6 times 10 to the minus 3. It's minus because we moved it to the right, right? And so now we can multiply both of these numbers. The first step is multiply the coefficients. So we have 3 times 6 times 10 to the 4 times 10 to the minus 3. 3 times 6 again is 18. 10 to the 4 times 10 to the minus 3 is what? Right, so this is going to simplify to 10 to the 4 plus negative 3, right? So that should be 1, right? 4 plus negative 3 is the same thing as 4 minus 3, which should be 1. So this then goes to 18 times 10 to the 1, we rearrange it, huh?
You have to put the one.
You don't have to put the one. A one.
Are you supposed to subtract it when you're dividing?
Oh, you're right. You're right. It's dividing it. Okay. Yeah, I appreciate the correction, but next time you guys could let me know a little early. What's up? Say that again. I think that one's still. Oh, I wrote them different up here. Okay, so we're just all over the place on this problem. All right, so we'll go by what's on there. But you're right. That would be 10 to the 5th. So this is our division signs now, all right? And so it still works the same way. We just replace all of the signs, multiplication signs, and then we'll start from then. We'll start from here. Okay. Oh, one more division sign. Oh wait, that's not a division sign. You keep that the same. All right, so it's 3 divided by 6 times 10 divided by 4. I'll write this neater. 3 times 10 to the 4 over 6 times 10 to the minus 3. This is the same thing. So we have 3 divided by 6 times 10 to the 4 over 10 to the minus 3. This is the same thing we did before, just rearranging the parentheses. 3 divided by 6 is what? 0.5. And now we have 10 to the 4 minus 10 to the 4 divided by 10 to the 3, which is 10 to the 4 minus negative 3, right? What happens when we have two minus signs like that right next to each other? They cancel out and they turn into an addition sign, right? So that becomes 0.5 times 10 to the 7. All right, and are we done here? I wish, me too, because this problem went on a nice windy path. Huh? I was trying to keep you guys on your toes, so. I'm just surprised I got almost all the way done with it before someone said something. All right, so now we have to rearrange it, right? Why do we have to rearrange it?
It's not 1.
The coefficient is less than 1, right? And so our decimal place is right here. Where do we move it? To the right. And if we move it to the right, what's going to happen to the exponent? We have to subtract 1 from here now, right? Because we move it to the left, right? We had to add 1. If we move it to the right, we're going to have to subtract 1 here, right? So this is 1 spot left minus 1 here. So this would then become 0.5. It would become 5 times 10 to the 6. That's not a minus 6, that's just a regular 6. Draw that neater. All right, and so the general trend, when you take a number and you divide it by a number that's a lot smaller than 1 or smaller than 1 in any case, it's going to be increasing in size, right? So we start off with 30,000, right? And what we're left with is something on the order of 500,000, right? So 30,000 divided by a small number becomes a large number. And you can follow this side of this slide. That using that notation is fine. It's just a little bit more confusing. This is easier to look at here, in my opinion. All right. Any questions on that? So I know that one is a little bumpy, but. Question? Anai? From this right here?
Yeah.
Yeah, you can just start from right here, yeah, because this is like, I just put, this is just because I already wrote it as multiplication, so I just changed it to a division sign, but this is easier, you can just start from right here. Ultimately, like, writing every single step is important for your own line of thinking. The work that you guys are required to show is just enough to show to show me that you understand what steps you're doing there. Right? Tyron? Yeah, so when you have two exponents that you're dividing, so if you have like, and they have to be the same base, right? When I say base, that means it has to be the same number that has the exponent, right? So when you're dividing them, two numbers of the same base with different exponents, you take the exponents and you subtract them from each other. Mm-hmm. When you're multiplying them, you add them together. And that's just an identity of how exponents with the same base work out. And it's actually because if you wrote it out 10 times 10 times 10 times 10, which is 10 to the 4 divided by 1 over 10, 1 over 10, 1 over 10, 1 over 10, that's where that actually comes from. But adding and subtracting is an easy way to remember for multiplication and division. Okay. All right, so this one's a little different. Let's see if you guys can figure it out. So how would you calculate 200,000 squared, right? So we did addition and subtraction. And so the rule for exponents is if you have something to the power a and all of that is raised to the power of b, what does that do to the exponents? Does anyone remember? Sam? You multiply them together. So that is equal to x to the a times b in the exponent. So the first step is still going to be converted to scientific notation, then write all of that squared, and then you can use the same identities that we have, splitting it up. The coefficient squared times the exponent squared.
So 2 would be which one? A or B?
So in this case, first write it in terms of scientific notation, right? So in scientific notation, what is 200,000? So do that step first. Right, because this is all of this squared. We want to write what's inside the parentheses I just write the scientific notation for that first. So 200,000 is what in scientific notation? 2 times 10 to the 5th, right? And then all of that gets squared. Another identity is if we have x times y squared, this is equal to x squared times y squared. That's another way that we can simplify things. So we can deal with the coefficient and the exponent separately under the square right here. So this we can simplify to 2 squared times 10 to the 5 squared. So this is how we get to this step. And the second identity is how we're going to deal with this expression right here. So what is 10 to the 5 squared? 10, yeah, that's what it ends up being. It becomes 10, oops, 10 to the 2 times 5. And 2 squared is 4. 2 times 5 is 10, so you get 4 times 10 to the 10. You're not going to see this calculation or this type of calculation as much early on, but I'm just introducing it because you will see this later. Right, and are we done there? Do we have to rearrange it all? Nope, because the coefficient is in between 1 and 10, right? We don't have to rearrange it all. Okay, all right, any questions on that? And again, we're doing just kind of review of some of the mathematics we'll need for the course. We'll also, as we see this in actual examples, right? Like it's easy when it's a math problem. Solve for this, you know, or use this to calculate these two numbers. But in practice, right, if we're actually looking at a physical problem, it can be a little harder to remember these steps and these identities when we're dealing with actual physical variables, right? So we'll talk about that more as we approach these topics in chemistry itself. Okay, and so the last thing I want to mention is some other mathematical concepts that we will see are exponentials, and these are the two identities that I just gave you to do the previous one, right? So that is like x to the a to the power b is equal to x to the a times b. And those can be positive or negative numbers. We can also isolate variables that have exponents. And again, I'm just introducing this right now. We're not going to go through in-depth problems of doing this. So we can isolate variables that have exponents, right? So let's say we have 49 is equal to x squared, right? How would we isolate x there? Okay. Yeah, you take the square root of both sides, right? So we can take the square root of both sides. Square root of 49 is 7. So you get x equals 7. Technically, x equals plus or minus 7 there because it can be negative or positive 7. And we see this symbol a lot, the square root, but it can be any power. It doesn't have to be just squared because what the square root is, so we have 49 equals x squared. Taking the square root is the same thing as raising it to 1/2 power. So this is the same thing as raising it to the 1/2 power, right? And when we have an exponent of an exponent, what do we do with them? Right? When we multiply two exponents, we add them together. An exponent of an exponent, we multiply these two values, right? So this is equal to 49 x, oops, I'm gonna leave the other parts in red, x2, and it's gonna be times 1/2 raised to the 1/2 there. 2 times 1/2 is equal to 1, right? It's the same thing as saying 2 divided by 2 is equal to 1, right? And so this gives us the same answer, x equals 7. The only thing I'm highlighting here is that the square root is used for squares, but what if it was x to the 3rd power, right? Then you would have to do 1/3 of both sides, right? And that, you're not going to see that a whole lot, but you can plug that into your calculator if you had to. I wouldn't expect you to know the cube root of, I don't know, 16 or something like that. Okay, so that's one way we can use exponentials, and that might show up in the future when we talk about acids and bases. And one thing that'll definitely show up when we're talking about acids and bases are logarithms, right? So these are the inverse of exponents. And we have two types that we can use generally. it's the natural logarithm and usually base 10 are the two, right? So we have ln, the natural logarithm, and log, which is, you'll see the 10 there, log base 10. This is base 10 logarithm. And the purpose of logarithms is that if we raise something to a specific power, let's say we have, I'm going to write it up on the board here just so that it doesn't get too low. Let's say you had something like 15 is equal to 2 to the x, right? This is a weird looking algebraic equation, right? And the logarithm does the inverse of an exponential here. So when we take the log base 10 of both sides, we get the log base 10 of 15 is equal to the log base 10 of 2 to the x. And the identity, or the purpose of this, is because when we take the logarithm of something with an exponential, it moves that exponential outside here, right? And so it becomes x logarithm 2 is equal to logarithm base 10 of 15. And this looks, okay, there's a lot of letters in here and variables and numbers and it's like what's going on. But these are just things that you plug into your calculator. Logarithm, you just plug in 15 to your calculator and you hit logarithm button. And it'll spit out a number for you. So this is really just a number here. And that's just a number. So then we could isolate x the same way we normally do, where you have log base 10, 2, log base 10 of 2. Those cancel out on that side, and you get x is equal to logarithm 10, 15, logarithm 10, 2. And that just, when you plug that in, it'll just spit out a number for you. Right? So this will show up not till nearly the end of the semester, what we're just talking about right now. And what does the logarithm do? The logarithm just asks the question, if we had something log 15, it says 10 to the what equals 15. Right? So logarithm base 10 of 15. This is like interchangeable of saying 10 to the what is equal to 15. Right? That's the question the logarithm is asking. Its mathematical purpose is just the opposite of raising something to a specific power, but what it's asking is 10 to the what is equal to that power. Okay, so these will pop up when we do acids and bases because the pH is defined based off of a logarithm. Log base 10 means 10 to the what. Natural log just means the special number e, which we're not going to get into. E to the what is equal to whatever that is. All right, and so we might have to do a little bit of algebra involving logarithm once we get to acids and bases. But the idea here is we're just trying to get rid of exponents, and that's why we use them. It looks complicated, but it's really just a button you press on your calculator to spit out a number for you. Like, I would never expect anyone to know what the logarithm base 10 of 15 is. Okay. So these are just a couple other concepts that we'll see, and these ones we'll go, review more as we approach topics like that, right? So you get more practice with that. Probably the next couple weeks we're not going to talk much about them.